Hello everyone, I'm Xusheng from the University of Hong Kong. Today I present Eges, the first efficient and DOS-resistant consensus protocol for large-scale permission blockchains. This is a joint work between the University of Hong Kong, SUS Tech, the Hong Kong Polytechnic University, and Huawei. Blockchains are widely deployed because its security guarantees enable mutually untrusted parties to share data. Nodes in the blockchain run on a P2P overlay network and use a distributed consensus protocol to agree on a totally ordered sequence of transactions. Blockchains can be permissionless or permissioned. In a permissionless blockchain, nodes can join and leave at any time, but it is usually tightly coupled with a cryptocurrency mechanism, and the coins must have real-world value to incentivize nodes to contribute and follow the protocol. In contrast, in a permissioned blockchain, nodes must go through an explicit authentication process before joining the system. As permission blockchains are usually decoupled from cryptocurrency, they are more suitable to deploy more general and cryptocurrency-irrelevant data sharing applications. Moreover, thanks to the explicit member list, permission blockchains can leverage efficient BFT consensus protocols for higher performance. Therefore, we focus on permission blockchains in this work. However, as existing permission blockchains designate a static and explicit committee to achieve consensus for all nodes. When a permission blockchain is deployed at large scale on the internet or over IoT devices, the blockchain is vulnerable to DOS attacks or partitioning attacks targeting this committee. Since from any node's own perspective, it cannot determine whether it is DOS attacks or network partitioning attacks that makes a remote node unreachable. We handle these two attacks altogether in this work, and call them targeted DOS attack. As illustrated in this example, even though there may be hundreds or even thousands of nodes in the system, as long as most of the committee nodes are attacked, or the network communication among them is attacked, the whole system cannot make any progress. Unfortunately, this committee size is usually very small for efficiency reasons, and although there exist scalable BFT protocols running on more nodes, these protocols designate a small number of fixed nodes who handle critical tasks like collecting signatures. Attacking these nodes greatly downgrade the system's performance. As far as we know, Algorand is the only blockchain protocol that can tolerate such attacks. However, Algorand is designed for permissionless blockchains. It is far less efficient than existing permission blockchains. We owe this DOS vulnerability to the static and explicit committee design of existing permission blockchains. Therefore, to solve this problem, we design a new dynamic and stealth committee abstraction. Eges use different groups of committees for different blocks. Conceptually, even if the committee for block N is attacked, Eges can switch to another committee for block N+1 to move forward. More importantly, the selection process must be random and unpredictable to avoid an attacker always targeting the nodes that are going to be the next committee. Eges also makes the committee stealth by making their identities unknown to the attacker before they send out protocol messages. Moreover, when the committee are communicating through network messages, their stealth identities are compromised. So, Eges use fake committee nodes that behave the same as the real ones to cover the real committee nodes. To realize this new abstraction, Eges leveraged the TEE hardware feature, which is also widely used by existing blockchain systems like REM and Intel PoET. TEE provides an isolated space called enclave on the CPU, and TEE guarantees both integrity and confidentiality for code and data in the enclave. Eges leverage the code integrity property to ensure the randomly selected committee nodes follow Eges protocol. Otherwise, it is almost unreal to guarantee the honesty of a randomly selected group of nodes. Eges also leverages the data confidentiality property to make the committee's identities stealth. Now we sketch Eges detailed protocol. Eges selects one distinct stealth committee for each block index. Each committee contains exactly one proposer to generate a block proposal and to drive the consensus progress. Each committee also contains a fixed number of acceptors and a group of fake acceptors and arbiters to cover the committee nodes. Eges makes the committee selection process unpredictable and non-interactive to make the committee's identity styles. Specifically, Eges let the proposer of block n-k to select the committee for block n and encrypts the committee identities within the block. The proposer creates one certificate for each committee member by encrypting the concatenation of a predetermined byte sequence and the nonce, which is selected node's public key. After confirm block n-k, each node tries to decrypt the certificates one by one and confirm its committee membership if it can match the predetermined sequence. Note that the selection and encryption process are conducted within the proposer's TEE, so the proposer cannot control or know the results of the selection. The decryption process is also conducted within each node's TEE, because each node's private key is only visible within its TEE enclave, and the node will generate signed protocol messages only after confirming its committee membership. A non-committee node cannot pretend to be a committee member in Eges. This committee selection mechanism ensures stealthiness because only a committee node's enclave knows whether it is a committee member for a given block. After a committee is formed, Eges can start to achieve consensus on a block. For simplicity, we omit fake committees when describing the protocol. We make the normal case protocol as simple as possible to achieve high efficiency. First, the proposer broadcasts its proposal to all nodes via the P2P overlay network. On receiving the proposal, each node catches it and replies an ACK if it is an acceptor. On receiving quorum ACKs from acceptors, the proposer broadcasts a final message to confirm the block proposal. However, a key challenge stems from the cases where a node cannot receive the next block in time. For liveness, the nodes cannot wait forever because the committee nodes may fail or are under DOS attacks. Note that although the committee's identities are stales, the attacker can still randomly get some nodes to attack, and the probability for him to luckily find the committee nodes is non-zero. This is also why we need to rotate the committee even with the stealth committee abstraction. The challenge here is that from any node's perspective, it cannot distinguish between the following two cases. In case A, the proposer for block n fails before sending out its proposal, so the consensus on block n is never achieved, and therefore all nodes can append an empty block to take place. In case B, the consensus for block n is achieved, and most nodes can confirm block n. However, due to network errors, the nodes on the right side does not receive block n, but this time they cannot append an empty block because it will cause inconsistency. However, for any single node, it cannot determine the two cases. Existing consensus protocols on static committee leverage the quorum intersection property to distinguish such two cases. But this approach is not viable in Eges, because in Eges threat model, Eges want to achieve liveness even if most nodes of a committee are under DOS attacks. To address this challenge, we design a new protocol based on probability theory. We only show the math intuition of the protocol here. Our paper contains detailed pseudocode of the protocol step by step and a formal proof. In Eges, since each block index has exactly one unique proposal, we have only two choices for this block: confirming this proposal or confirming an empty block. As long as we can make the probability that the two nodes select opposite choices to be overwhelmingly small, we can ensure safety. Recall that the proposer broadcasts its proposal over the P2P network, and the acceptors are uniformly selected from all nodes. So, Eges regards the acceptors as a sampling of the dissemination of the proposal in the P2P network, and the number of acceptors having received the proposal follow hypergeometric distribution. Here, the number of nodes M, the number of acceptors NA, the quorum sets Q are all constant, and the only variable is P. Note that the acceptors' identities are stealth, so an attacker cannot selectively drop proposals to an acceptor to break this sampling result. Since confirming the proposal requires at least a quorum ACK from these N acceptors, The larger P is, the higher the probability that the unique proposal is confirmed. On the other hand, to confirm the block as empty, Eges does multiple rounds of sampling on different groups of nodes, and requires that each group has a quorum replies saying never received this proposal. This implies that the dissemination rate P of the proposal should be very small, because every time I ask a random group of nodes, no one receives it. In other words, the smaller P is, the higher the probability that the empty block is confirmed. Since this two inconsistent case requires P to grow on opposite directions, the probability of them happening together is already small. We can control the value of Q, NA, and D to make the probability of two inconsistent cases happen together to be overwhelmingly small. Eges default parameter ensures that the probability of inconsistency is lower than 10 to the power of -9. And we also include the correlation of the parameters in our paper. Overall, Eges is resistant to DOS or partitioning attacks targeting committee nodes, because Eges make their identity styles before and during they are achieving consensus, and Eges dynamically rotate the committee for each block. Eges is also efficient, because its normal case is designed to be lightweight, and its failure case leverage the speculative merit to let the repetitive check of unconfirmed block run in parallel with the consensus of future blocks. We implemented Eges using Go Ethereum's codebase, and used Intel SGX as the TE hardware. Eges also carries protocols for handling attacks targeting the TE, like forking attacks. Our evaluation was conducted on both our cluster and AWS. Each node was run within a Docker container, and we spawned up to 10K nodes. We set the RTT between two nodes to be a random value between 150 and 300 milliseconds to emulate the network in the internet and among IoT devices. We have 5 evaluation questions, but we only focus on the first 2 due to time limit. We compared Eges efficiency with 9 relevant protocols. The result shows that, compared to Algorand, the only known DOS-resistant protocol but designed for permissionless blockchains, Eges achieves much higher efficiency. Compared to existing permission blockchain protocols that are based on static committees, Eges achieved comparable efficiency, but Eges adds the DOS-resistant feature to this protocol. For DOS resistance, we first conducted DOS attacks targeting the real or fake committee nodes, because as an attacker, we could not distinguish real and fake committee nodes. The system could return to normal throughput after a few seconds on our attacks, thanks to Eges' new protocol. We also created network partitions among all nodes. The larger partition could continue to make progress, and the small partition just hung and waited. The fluctuation was because a portion of the committee nodes of some blocks were in the small partition, so the consensus on this block went into the failure case of Eges protocol. The system recovered after the network reconnected without causing inconsistency among nodes. Now we conclude. Eges is the first permission blockchain's consensus protocol that uses the new dynamic and stealth committee abstraction to resist DOS attacks targeting committee nodes. We believe Eges can facilitate the deployment of a large-scale permission blockchains running on the internet and IoT devices. Eges code is open sourced. Thank you for listening, and I'm happy to take questions.